This presentation about time mainly deals with cosmology and serves as an introduction to the fractal topology of spacetime theory. A relatively simple observation has led me to question much of the Big Bang cosmology regarding measurement, time and position. I hope this presentation will make accessible the theoretical ideas that are proposed here. We see fractal patterns everywhere: clouds, ferns, snowflakes, etc. And with mathematics we can create natural looking special effects scenes for films or create beautiful dynamic patterns. But what I really want to demonstrate is how fractals are at the very heart of space and time. Wesselschleifer was an astronomer who in 1912 was charged with the task of obtaining spectrographs of spiral nebulae. We would now call these other galaxies. He found that most had a Doppler-like redshift, indicating that they were moving away, but after seeing Andromeda with a Doppler blue shift, and therefore moving swiftly towards us from the other direction, concluded that we had a movement through space in that direction. Andromeda is more the exception than the rule, and Alexander Friedmann assumed that the universe was dynamic, and following the axiom of the cosmological principle, found the most general and realistic solutions to Einstein's equations, and was the first to predict mathematically an expanding universe. Georges Lemaitre also predicted an expanding universe from Schleifer's observations. He predicted that there was a linear distance-velocity relationship, and this relationship is now referred to as the Hubble Constant. In 1929, Edwin Hubble, using the world's largest telescope at Mount Wilson, California, made more accurate observations and found that the recessional velocity of distant nebulae were proportional to their distance, unaware that it was something already predicted by Georges Lemaitre. A common analogy for the expanding universe is this balloon with buttons. The balloon represents the space stretching between the galaxies, and the buttons the galaxies whose size appear unaffected. The buttons separate but do not move across the surface of the balloon. They appear stationary, relative to the space they occupy. Lemaitre extrapolated by reversing the effect backwards through time that the universe had a finite age, and that it had emerged violently from a primordial atom in a very hot dense state, and his fireworks theory was the precursor to the Big Bang theory. However, the following thought experiment based on real data has led me to believe that the apparent recessional velocity is not a real movement at all, or a positional change, and that the Hubble constant depends upon your frame of reference. Here, on Earth, gravity is slowing down time, and this effect diminishes the further away from Earth we go. Travelling at speed will also slow down time, and although the Hubble Space Telescope is orbiting at 353 miles above the Earth in a low Earth orbit, it has to be travelling at 17,500 miles per hour just to stay in freefall, making the time dilation effects greater than on Earth, and so it experiences less time moment to moment than Earth. This SYNCOM 3 satellite sits in a geostationary orbit and rotates with the Earth, moving slower than Hubble and now 22,250 miles above the Earth. Here time runs faster on the satellite, and it experiences an extra 45 nanoseconds relative to time on Earth every complete revolution. With the speed of light always being measured the same at the satellite and on Earth, with that extra 45 nanoseconds, light from the satellite can travel an extra 44 feet 2 inches. Although measured the same, the speed of light is relatively faster on the satellite due to a synchronous time and distance asymmetry. The meter, our SI unit of distance, is now based upon the speed of light, and so any ruler is actually defined by the elapsed time a photon would take to transit that ruler. So a ruler on a satellite where there is more elapsed time would be relatively longer than a ruler on the Earth with less elapsed time. With relatively shorter meters on the Earth, the satellite is relatively further away. This is a distance asymmetry and not a positional asymmetry, and that's very important. So the Hubble Space Telescope and Earth observers will measure distant galaxies further away than an observer, say, on a geostationary satellite. The next thing to consider is that if our measuring rods are relatively shorter on Earth, then so too are the atoms that make them and everything else on Earth. To explain why the universe appears to be expanding for all observers in the universe, all that we need to consider is that all atoms are shrinking isomorphically, that's evenly in all dimensions, as a fundamental property of time, and that time is slowing down relative to the past for all observers in the universe. Where we have greater time dilation, distant galaxies will be measured to be further away and moving with a faster recessional velocity, and therefore measure a higher Hubble constant. So the Hubble constant is therefore a measurement of the rate of time for the observer. Counterintuitively, the relative duration of a second becomes shorter as time slows down. Fractals are inherently counterintuitive. You may wonder how I can entertain the notion that the speed of light can simultaneously have a faster and slower duality, when the velocity is always measured the same. In this slide, we have 3 different time scales. When a photon travels from A to B, time is faster at A in the past than at B. The photon experiences no time at all, so the photon jumps from A to B in 0 time, and that's infinitely fast relative to A. Yet, relative to B, it is stationary or infinitely slow, as it is already there the moment it left. This makes the speed of light transfinite. It's in a superposition between the past and the future, until, that is, it is observed at position B, where the observer determines the velocity as c, the constant speed of light. So the speed of light is always measured the same relative to time and distance at the observer's scale. We all know the story of Alice's adventures in Wonderland. She has just drunk the bottle contents and is about to shrink. But before she does, I'm going to give her a couple of measuring rods to help with my analogy here. When Alice shrinks, she remains standing on the same spot. So Alice and the key do not change their position. We can demonstrate a distance asymmetry. Although she is now further away relative to the key, Alice is even further away when measured with her shrunken measuring rods. If matter is shrinking like Alice, this isomorphic transformation can produce a Doppler-like redshift of the light from a distant galaxy. That's my cat. You see, we normally think that the moving galaxy was the cause of the redshift. But if our measuring rods have shrunk relative to the rods on the galaxy when the light was emitted, then we have the same effect as a Doppler shift. Although space is not stretching and the galaxy is not moving, the apparent recessional velocity is still taking the galaxy further beyond our reach, like a real movement. Just ask Alice when she's small. To us then, that's in the red circle, all my observers are in these red donuts. All galaxies at great distances are moving away with a linear increase in velocity of about 70 kilometers per second per megaparsec. Now, a parsec is about 3.3 light years, so at 1,000,000 times further at this megaparsec is pretty far out, And if we draw a circle with a radius of 1 megaparsec, anything at that distance will have an apparent recessional velocity of about 70 kilometers per second, twice that at 2 megaparsec, and so on and so forth, with a linear progression in speed with distance. And with our current understanding, everything is moving away from everything like this as space stretches. But if our time, distance and size scales are changing over time, then the expansion would be like this, with no real movement attributed to it, and with no limit to the size of our universe. The apparent recession will become faster and faster, and eventually reach the speed of light in all directions. And this is called the Hubble sphere, and it's even faster beyond the Hubble sphere. Everything in this slide is shrinking by the same amount as a toy model. The visual effect is to change the distance scale for all observers. The shrinking Hubble sphere is relative to the observer in the middle of the slide. Space is absolute, and you can see that galaxy A and B do not change their position, but relative to galaxy A, B is receding faster than the galaxies closer to A. The effect is just as though space was expanding. But there are subtle differences. It does not include any peculiar movement, apart from the hidden peculiar movement that stars have within the galaxies that make them also shrink. And I'll be explaining that in a later slide. Note, this is a privileged view, seeing all at their moment in time, but an observer sees distant objects as they were in the past, with a comoving size scale. The Hubble sphere is a limit to the future influence of light leaving the observer. We can see the more distant galaxies, even though they are receding faster than light and faster, because they are in our past, and so larger in scale, and that includes their Hubble sphere. Therefore, our position now was within their Hubble sphere when their light left them. Of course, it is the same for all distant objects that we see from any direction, including the very first atoms and the light that they emitted, that we now see as the cosmic background radiation. How fast we are shrinking is the opposite to the expansion. So scale down the volume of space with 1 megaparsec to the volume of the Earth with a radius of 6,371 kilometers, and the 70 kilometers per second become 0.46 millimeters per year. So Earth's diameter will be relatively smaller year on year by about a millimeter, all unnoticeable and unmeasurable to the occupants of Earth. So going backwards in time no longer gives us a shrinking space, or a positional change for the galaxies like this. Every atom would be a primordial atom, and about the size of a beach ball, each in their unique and infinitely many positions. As the galaxies shrink, they leave behind the space they occupied. Because space is absolute, all changes in actual position are peculiar movements due to the local effect of gravity. The mean density of the universe stays the same holistically, but the effect gravity has can increase locally as the atoms shrink. Gravity on the Earth increases at the surface, as the same mass occupies less and less space over millions of years, so the balloon analogy no longer works. With a constant mean density, space remains flat. With current theories, there are three possibilities for the evolution of the universe. With the expansion as a constant, much depends on the average density of the universe. Too high and acting as a brake, the expansion will go into reverse. The universe heats up again as the matter heads towards the big crunch. Just right, and the universe expands forever. And this is what the Wilkinson microwave anisotropy probe data is showing us. If this is the case, it is quite remarkable after all this time. It has been compared to balancing a pencil on its point at the beginning of time, and it's still be standing there now. If the mass density is too low, then the universe is open, and we head for the big freeze with no end. Parallel lines diverge in a strange hyperbolic space geometry. In this model, space does not expand. The average density is as it always has been since the Genesis moment. All matter is shrinking relative to absolute space, but the mass remains the same as we measure distances relative to our shrinkage. Space is flat on a large scale and over time. At the Genesis moment, matter has no immediate inertial movement, and with no push involved with the apparent expansion, the pencil analogy would be that it is dangling from a thread, and that is very stable indeed. Soon after Sir Isaac Newton had published Principia, the Reverend Richard Bentley proposed the question, since gravity is always attractive and never repulsive, then any collection of stars would naturally collapse into themselves. He argued that any finite collection of stars would end up as one fiery superstar. He also pointed out that if the universe were infinite, then the collective force in every direction would pull all the stars apart. In this theory, though relative to absolute space, stars can have a hidden peculiar movement whereby the distance scale shrinks at the same rate as gravity moves the stars together. If there were a void to the right, then that void would appear to expand or stretch. This is how current theories see the evolutionary age of the universe. The cosmological principle is an axiom that the universe is homogeneous and isotropic, viewed from a large scale. That means it should look and act the same for any observer from anywhere. And everything here looks the same with accelerated expansion. All the universe looks younger, less developed here. Things start to become visible here, and everything is in the process of cosmic inflation here. But the expansion over time does not adhere to the cosmological principle. If it did, this graph would look more like this. And I think it should. So when we look at the expansion as a changing distance scale, with space remaining absolute, even the time narrative of the universe becomes homogeneous and isotropic. Earlier, I mentioned a hidden peculiar movement that would explain why galaxies themselves shrink with matter. And for this, we need to go back to our old friend, the geostationary satellite. The measured orbital distance remains the same. Yet, during each orbit, the Earth and the satellite are shrinking, and therefore, relative to the past, the satellite has moved a fraction closer to the Earth. This is a real peculiar inertial movement towards the Earth. This makes a subtle difference to gravity as well. On the surface of the Earth, gravity will be getting stronger, as I said, over vast amounts of time, as the same amount of mass occupies less and less space. The strengthening of gravity and this peculiar movement locally towards the centre of mass should be extended to all gravity-bound objects, like a galaxy, and the opposite effect will be noticed in the voids between galaxy clusters. Now, gravity is still positive there, but decreasing due to the hidden peculiar movement of galaxies as they migrate away from the voids and towards the gravitational focus and form the fractal distribution patterns that we see when we look at the distribution of matter on a very large scale. I believe this throws some much needed light on the subject of dark matter and dark energy. Back here on Earth, life often forms fractal patterns like this tree fern. Each frond contains many self-similar smaller copies of itself that we call levels of description. So this would be the first level of description, this would be the second level of description, and this the third. When stacked like this, they become a nested set. The progression is known as the fractal depth, with the lowest level called the fractal prime, in this case the fourth level being the leaflet. When we look at the evolution of stars, we can see similar levels of description patterns, with the first generation stars being the behemoth population 3 stars that form from pristine gas clouds. The next smaller are more dense, containing some heavier elements forged in the earlier stars, and the third generation will include our Sun. And I see the fourth level as the more compact objects like white dwarf and neutron stars, etc. The narrative of the universe unfolds in time. And as time slows down over time, duration for all observers everywhere, relative to their past, diminish in scale, along with the relative dimensions of all atoms, and this shrinking clock is an analogy for this. Time has a fractal depth, and similar to the photon, time is infinitely fast at the start and infinitely slow at the end, and has an undeterminable transfinite duration, or eon of time. The rate of time being infinitely fast at the genesis moment means that the duration between two moments is also infinite, and therefore a continuum, or what some may refer to as a white hole singularity. Every moment a new time eon will emerge from this. Eventually, the duration between two moments become infinitely short, and time reaches the fractal prime for each eon of time in a black hole-like singularity, where time stands still, completing a fractal loop with the singularity having a black and white duality, or two poles, a bit like a magnet. So, when our eon of time emerged, it was not alone. It was part of infinitely many, each with their entrances and exits. The universe has always existed, by which I mean the totality of existence and not just our infinite part. The singularity is at the core with two poles like a magnet. But magnets are not lopsided like this. The lines of magnetism have a symmetrical parity like this. But is this a parallel universe? Well, maybe. But I think it could solve the baryon asymmetry problem. At the genesis moment, an equal amount of matter and antimatter should have emerged. The singularity in this case becomes the generator conserving the symmetry and charge parity, a natural assumption but one not afforded by current theories. So, at the genesis moment, every matter eon of time has an entangled antimatter eon of time, both infinite and thus separated until they recombine at the singularity. To make this consistent to the many worlds interpretation, we merely have to make this analogy here three-dimensional and complete the field with this complex torus. And so we have infinitely many eon pairs emerging at every moment. Thank you for listening.